And before we start on multiple beam interference, let's look at Stokes relations. Well, this gentleman here, he is Sir George Stokes, and he's an Anglo-Irish physicist, so these relations are attributed. Credit is given to him. So we are going to look at the reflection and transmission coefficients. Basically, that's just the ratio of the amplitude of the reflected beam's electric field to that of the incident beam. And for the transmission coefficient, that will be related to the electric field amplitude of the transmitted beam over of the incident beam. Now let's look at Snell's law for an incident beam that is incident onto the interface that separates two media, that's N1 and N2. So look at the black one first, black line here. So this incident beam EI, we just consider the electric field amplitude. So when it gets, part of it gets transmitted, so that ET, the amplitude of the transmitted beam, will then be equal to TEI from what we have defined earlier, T. And the reflected beam will then have ER equals to REI. Okay. If we have a ray that is incident from the second medium instead, and coming along the path of that transmitted ray, so we then write it as TEI, then it gets reflected. Now this would be internal reflection, so we will then put a prime to denote that this arises because the incident beam comes from the second medium. Okay. Now, so then the transmitted beam would then be this one, which is T prime of TEI. Here will be R prime of TEI. Now, figure B actually shows the principle of reversibility. And so if we were to reverse all these rays, it should be valid because according to the principle of reversibility, using the same amplitude, yeah, but just reverse the direction. And in general, in figure C, in general, if we consider two incident rays on the interface, okay, so these two incident rays, so we consider this one that's coming here, so that will result in that blue dashed line that we considered earlier. And the other beam that is incident from this direction, see this one we're going to write here, REI, then will give us a transmitted ray. Now this from medium 1 to 2, so we will have T REI, and then the reflected one will be RREI, so R squared EI. Okay. Now, this should be valid upon principle of reversibility. So in other words, we're going to say that figure B and figure C, they should be physically equivalent. So what would that bring us to? So if you look at this, well, then we'll find that this term add on to this term would be equal to 0. Whereas this term plus this term should be equal to EI. So then the common here, EI removed. So in other words, we will then come to Stokes relation, which is T prime T will be equals to 1 minus R squared. Whereas over here, TT is common, we can cancel off. You'll find that R is actually equals to negative R prime. Now, this is understandable over this because your negative 1 can be written as exponential I pi. So in other words, the amplitude of the reflected beams for rays that is incident from either direction will have the same amplitude, but they will differ in a pi shift. Okay, they will differ in a pi shift. Now, this Stokes relation actually agree very well with results if we derive it using Fresnel's equation. But that will be another lecture much later. So from Stokes relation now, we would be able to then determine the resultant irradiance from interference of multiple beams in a parallel plate. Let's say we have a parallel plate which is basically that thin film, this parallel surface, and this N, this NF, and assuming that this is also air, which is N. So we have an incident beam E0 with amplitude E0, gets reflected, this external reflection, so RE0, forming beam 1. And then it gets transmitted, we have TE0, and then hits the bottom surface, it gets reflected. Now in this case, it's an internal reflection, so we use R prime. Hits here, gets transmitted. So in this case, because of this beam was internally reflected, so we will have a it was internally reflected, so we will have R prime of TE0, and then as it exits here, we have T R prime E0, and we have a T prime, okay? And then you have multiple reflections. So this one gets reflected. This is internal reflection again. So you get T R prime squared E0. Upon here, internal reflection again. So you get T R prime to the power 3 E0 and so forth. Okay. Now at this point here, part of this beam is also transmitted. So at this point where we have internal reflection, so it's coming from a denser to a less dense medium, so we will have T prime T E0. And here we will have T prime R prime squared E0. Here we will have this term multiplied by a T prime. Here we will have this term multiplied by a T prime. Now this is for rays that are transmitted through this parallel plate, and these are rays that are reflected, so there are multiple parallel beams that emerge from here and multiple parallel beams that emerge from here. Now all these, if we put a condenser lens, a converging lens, then we will be able to focus all these parallel beams, bring all these parallel beams to focus, and we will be able to observe the interference. Over here, so this is the one that is reflected and then get transmitted. So it will be T prime T R prime cube E0. This beam here would be T prime T R prime to the power 5 E0 and so on. Okay, so that's how we determine the portion of the electric field that get reflected, of those emerging beams from here, and here too we will be able to define the amplitude of the electric the field of the ray that gets transmitted. So this train will progress until the end of this the extent of this plate. Okay, so from the analysis of interference of the first two emerging beams, so the phase difference between the first two emerging with the successive beams, we have already done that for our two beam interference early part of this lecture. So that will give us a phase of which is equals to K delta here, phase difference, and then that path difference equals to 2 NF T cosine theta T. This is the transmitted angle. Now let's consider the incident ray to have the form E0 exponential I omega t. It's a harmonic wave. So the reflected ray in that case would be R E0 exponential I omega t. The second reflected ray would then be T prime R prime E0. The amplitude changes, but this function here also there is a phase shift upon reflection internal. This is external reflection. With respect to this, there would be a phase difference due to reflection. Respect to this, there would be another phase difference due to reflection here. So basically what we have is for ray 2, ray 3, ray 4, ray 5, ray 6, then the electric field of the emerging ray would be at the top, would all be written as such. Now, if we can sort of generalize this by looking at a pattern, you'll find that the nth ray, the nth reflected ray, will be equal to T prime R prime to the power of 2n minus 3 E0 exponential I omega t minus, now this will be n minus 1 multiplied by delta. Now, because nth expression, the one generalized nth expression will not hold for E1 because E1 did not go through, it did not traverse the plate, it just get reflected from the top surface. Okay, now we said we are superposing all these reflected wave components. So the resultant then would just be summing them up together. So you put in all the expression and you sum them up. So the first reflected ray stands alone here. Add on to the summation of all the others in a generalized term. And we try to find some common term and factor it out. Here we have this common term, we factor it out, E0, and yeah, and we left with R here plus summation of T prime, R prime to the power of 2n minus 3 exponential negative I into n minus 1 multiplied by delta. And here we can then also factor out the expression that doesn't have the common multiplied application factor here that doesn't have the notation n here, so that then now you note we are summing from n equals to 2 to infinity. Yeah? So factoring out, it will look like this. Now, if we were to let R prime squared E negative I D to be represented by X, then we can then write this term, this summation term, just this summation term, we can then write it as X to the power n minus 2, which then can simplify to 1 plus X is a geometric series, plus X squared plus X cubed, and so on. As X is small, then this sum will converge and it will give you a final converged expression, which would be equal to 1 over 1 minus X. So having said that, we can now then express this term to be 1 over 1 minus X. So we put this term there. Still R plus this term 1 divided by 1 minus 1 minus X. So X is this one, so we substitute that over here. So we have this expression. Now substituting in now for some of this expression using Stokes relation, so we can then rewrite the red one using this and R prime using negative R. So we have this expression, and when you expand it out, it will look like this. And finally, you find that the electric field of the resultant of this multiple beam, when you collect all of them, would then be equal to E0 exponential I omega t into R1 minus exponential negative I delta divided by 1 minus R squared exponential negative I delta. Now irradiance is as you've learned, is proportional to the electric field amplitude squared. Okay, now squaring this one, you will be multiplying ER with its complex conjugate. So you write this term there, and then the conjugate will have a negative I omega t. Here will be positive ID. Here will be positive I delta. Sorry, and yeah, that will be it. And then when we multiply that out, it will these two terms in this bracket here. This and this will give you 1. So these two terms will then work out to be 2 into 1 minus cos delta divided by 1 plus r squared minus r squared, or 2 multiplied by 2 r squared 2 cos delta, which is this expression here. 2 we factor out. So we will have E0 squared 2r squared multiplied by this. That would be the irradiance. Related to the irradiance of the resultant from the multiple beam interference. Now, writing in terms of irradiance, and where we use II to represent the irradiance of the incident beam, then we can write it as instead of E0 squared, now we write it in terms of II, so that the ratio of IR divided by II will then be equals to this amplitude ER squared divided by E0 squared. So you find that the irradiance of, because why we write this? Because the irradiance of the incident beam is proportional to E0 squared. So using similar treatment, we can also obtain the transmitted irradiance. It will come to this expression here. And when we combine the transmitted irradiance with the reflected irradiance, combining this and this, you work it out, you'll find that it is actually equals to just the incident irradiance. So conservation of energy is satisfied because we have assumed that foam is not absorbing. Okay, so we have calculated the irradiance of the multiple beams that emerge reflected from the top surface, and the multiple transmitted beams that emerge from the bottom of that parallel film. So what are we interested in? We would like to know where are the minimum irradiance and where are the maximum irradiance, because we want to look at the interference fringes. So let's look at minimum irradiance in the reflected multiple beams. Now that will occur when cosine delta is equals to 1, then this will totally be 0. That's good, because then we have good fringe contrast. Now, so that will occur when delta equals to 2m pi, even multiples of pi. And then delta, which is the path difference, optical path difference, which is equals to 2t nf cos theta t. And this, if you relate it to the phase, it will be delta over k, and that should be equals to m lambda. So this will be the condition for minimum reflected irradiance. Now, correspondingly, the transmitted would be maximum. So IT over here, cos this one becomes 1. So you have 1 minus r squared, squaring that will be 1 minus 2r squared, which is here, plus r to the power 4. So numerator and denominator value will be the same. So you get 1. So you find that IT equals to II. So you get maximum transmittance. So how did we get that? If you look at the figure again with all those reflected beams that we have drawn, you will find that at reflection minimum, the reflected beams 2, 3, 4, 5, 6, and so on, they are all in phase with each other. All of them undergo internal reflection. Now look at this. This beam gets transmitted, one internal reflection, goes out, no phase shift. Second internal reflection, third, and then goes up, no phase shift, and then fourth and fifth, and then goes up, no phase shift. So all these have no phase shift, so they are in phase with each other. But the first beam itself has got an external reflection here, so there will be a phase shift of pi. So all this will then be out of phase with this the first beam itself. So hence the net reflected irradiance would be 0. That is at reflection minimum. So in other words, earlier on when we started lecture 13, we only considered the first two beams. So it worked well and it's justified from this argument here. So it was sufficient to just look at two beams. Yeah. Now the amplitude ratio of beam 2 to beam 1 would actually be equal to E2, which is T prime R prime E0 divided by R E0. Now T prime is 1 minus R squared. R prime can put it as R, and R also cancels off. So that leaves us with 1 minus R to the power squared, R squared. Now if R is very small, then it's about equals to 1. Yeah, it's almost equals to 1. So in other words, the electric field amplitude of beam 2 is almost equals to 1. So the further beams that emerge with more reflections will have very, very low irradiance. For example, in glass, N is 1.5, R squared is actually only 4%. So we have a 96% cancellation in that sense. So that's good. Now, what if we talk about maximum reflected irradiance? Now, that will occur when cos delta is -1. If you look at this expression, for this one to be maximum, that will occur when this is -1. This -1, you get 2, you get 4R squared over 1 plus R squared minus plus 2R squared, and that will be 1 plus R squared, the whole expression squared. So the IR would actually be equal to 2R over 1 plus R squared, the whole thing squared of the irradiance of the incident beam. Now, so this will occur when delta equals to odd multiples of pi. And then therefore, the path difference will be, which is written as 2n nf cos theta t would be equals to delta k, which would be equal, then in that case, it is all, when you write this, it should be equal to n plus half lambda. Correspondingly, then the transmitted irradiance would be minimum. So if you look at the expression here, when cosine delta is -1, that means the denominator is going to be larger. So when this is going to be larger, that means this term here, or rather this term here, this expression here would be the smallest value. So that's why we have minimum transmitted irradiance. So this parallel plate arrangement actually will be used in what we call the Fabry-Perot interferometer, which we will learn about in the next lecture. All right, so the learning outcomes from this lecture. You should, after going through this, you should be able to explain how interference fringes are produced in a thin dielectric film, and should be able to derive the equation to obtain dark and bright fringes of the interference that occur. And you should be able to describe applications for this. For example, we'll talk about anti-reflective coating, how to measure film thickness, and you should be able to explain and describe what's piezo fringes, and that is extended to formation of Newton's rings. And last but not least, you should be able to derive or define Stokes relations, and be able to explain, use it also, apply it to in multiple beam interference to derive expressions for irradiance of reflected and transmitted beams from a parallel plate. Okay, thank you.